All right. Well, let's get going. So welcome everyone to our very last of the semester, Science by Diverse Scientists Talk. This was our very first semester of this series, and I think it's been pretty successful. I certainly have enjoyed coming to all of these talks. We'll be continuing next semester, late January is when we'll have our first talk of next semester, and we'll continue doing them every other week. So for our final talk, I think it's sort of nice that we ended up having Arturo Martinez, who was actually a Cal Bridge scholar in the very first cohort, correct, of scholars?
Yes, that is correct.
So that I think is extra perfect and special. So Arturo did his undergrad at San Diego State and is now a PhD candidate at Georgia State University. And today he'll be telling you a little bit about the research he's been doing there. So take it away, Arturo.
Great, thank you very much. So today I'm going to be talking about my PhD work. Currently, the current imaging I've been doing throughout my PhD, and some kind of future concepts, or like a small test bed of what we can do for, to improve the current interferometric imaging that we have today. So that being said, I'll go ahead and begin. So I just like to note that for most of my PhD, I kind of been focusing on the software side of things. And so I just have a few science motivations here to kind of apply some of my interferometric imaging work. So kind of just go over, two objects here, or two sets of objects, an RSAV variable, Lambda Andromeda, some rapid rotating stars, and then so after that, I'll kind of talk about the future of interferometry, or where it can go. So first off, Lambda Andromeda, the test bed of for my interferometric code. What is Lambda Andromeda? It's an RSAVN variable. And these types of stars are binary stars. They essentially have their primary star that is very magnetically active, and usually they have a companion that's a low mass main sequence star. Particularly for Lambda Andromeda, this star is a single line spectroscopic binary that has asynchronous rotation with its companion, or with the orbital period of the binary. So what does this mean? Really quickly, the rotation period of the primary, 55 days, is not the same as, it's not tidally locked. So it's completely different than the binary period, of which is roughly around 20.5 days. I put some parameters up here so you could kind of get an idea of how big the star, or the primary star, actually is, and some of the characteristics. So why am I even kind of studying Lambda Andromeda in the first place, and why is it important for imaging? Well, if you could get good characterization of these types of stars, you can start to really understand things like get more precise measurement for exoplanetary work. This particular RSAVN variable is very, very magnetic, and so understanding star spots and constraining them, you start to understand, what type of exoplanets you're observing if you're observing other types of stars with spots as well. On the other side of things, more on the stellar side, you start to understand what type of dynamos these stars have. So whether it follows, exhibits star spots that are very similar to the sun or are somewhat different. In either case, we can explain, well, why are they behaving differently? Or we found a star that kind of has the same type of dynamo as our own sun. So kind of my first investigations kind of start there. The next set of stars that I'm going to be talking about, or these next set of objects, are rapid rotators. So these rapid rotators are stars that are spinning very quickly, that their equators start to bulge. And they actually spin very quickly, that they're actually reach around 90% of their critical angular velocity. So they're at the point where they maybe are starting to get ripped apart because of their rapid rotation. This rapid rotation also causes a phenomenon called gravity darkening. And so what you see as a consequence on these images here on the right is that the poles are actually a lot brighter than the equator itself. So for example, Andromeda, you could see that, some of these, the pole here is brighter, and you have a consequence of, gravity darkening here. Back in the 1920s, there was someone named von Zeipel came up with a kind of a crude way of trying to describe the temperature, the surface temperature variation across the surface of this star, of these types of stars. So he basically described that the effective temperature can be correlated to the local surface gravity, to some, to exponential power depending on the type of star. So that way you could kind of see, okay, this has, exhibits, a lot of gravity darkening or just very little. So again, why are these types of stars kind of important? And why am I even investigating these in the first place for my PhD? What I have here is plots of an HR diagram of and evolutionary tracks for different types of stars here. So different stars of different masses, ranging from 9 solar masses all the way to 120. So what you'll see here is that I have, for one given mass star, you have 2 different evolutionary tracks. So started ages, it starts here on the 0 age main sequence, and then slowly as it ages, kind of changes temperature and luminosity. The solid lines that you see here are stars that are not rapidly rotating. So stars that, still spinning, but not as fast as these rapid rotators. They don't have they don't reach the 90% critical angular velocity point. And these dotted lines here are show the evolutionary tracks for these rapid rotators. And you could start to see for all of these different mass stars that they really evolve differently than their non-rapidly rotating counterparts. In addition to that, these rapid rotators actually have a lot more mixing than their kind of spherical counterparts. This mixing allows you to have more hydrogen to the core and allows you to fool the star even more, and changes how the star starts to behave. Hence these different evolutionary tracks here. So how am I how am I getting images of all this of all these stars? Well, I'm from Georgia State University, and Georgia State has really nice access to a nice observatory called the CHARA array. So what is CHARA? CHARA is an interferometer with 6 telescopes configured in a Y configuration. So I have them, the telescopes kind of circled here. And CHARA currently has the world's largest angular resolution, or provides the world's largest angular resolution in the infrared. So you could go anywhere from around, get, baselines of 30 meters all the way to 330 meters. So what do I mean by baselines, and why this is important for interferometers? If you take a step back and look at a single telescope, the resolution that you get goes as lambda over the diameter of the telescope. It's a little bit different for interferometers. You get something like lambda goes divided by the baseline, where the baseline is essentially the distance between 2 different telescopes. So here, if we, because we observe in the infrared, and this example for our purpose here, if we take the longest baseline, you could start to measure objects down to the milli-arcsecond regime, and the kind of the limiting resolution for H-band is around half a milli-arcsecond or so. So you could really start to see things, very, very small things up in the sky. To kind of just give an analogy of what all of this is that it's really akin to if you have a small telescope on here on Earth, and you try to read a newspaper that's about 100 miles away. You could start to read letters that are about 2 millimeters wide. So it's, again, start to see things at a very, very small scale. One thing that I have to note is that you do get the angular resolution of a 330-meter telescope if you use these large baselines, but you don't get the sensitivity because, again, you're losing all of the light to the terrain and you're only capturing a small amount of light, but you still get that angular resolution. So kind of now let's kind of move into how interferometry works and why, how we get from interferometric measurements to an actual image. So let's start with the schematic that I have here on the right. We have a source very, very far away. It's providing light to us and eventually gets to two different telescopes. So just, you know, interferometer with just two telescopes. The light will reach telescope 2 first, and then after some time, based on this geometrical delay, you'll get to the first telescope here. Light will be relayed all the way to the beam combining lab, but because you have telescope 2 getting light first before the other telescope, you'll need some sort of internal delay in order to compensate that, so that way you get an actual quantity that you can that it's useful for you. So you basically provide these movable delays somewhere to compensate for this geometrical delay up in the sky. And then the final result is that you get interference patterns because the light reaches the detector at the exact same time. Okay, so let's look at, you know, the chart right here, one example of a telescope and how the light is propagated from the sky all the way down to the beam combining lab. Let's pretend we're observing in the night. Light comes in here through the primary, bounces off the secondary, does a few more kind of reflections here internally, where it finally reaches the bottom of the telescope and gets sent through this, this vacuum pipe to the beam combining lab. From here, light comes in through underneath to some mirrors acting depending on how much delay you want. Will reflect up, hit some more pipes where it finally reaches a cart on this rail system that you're kind of seeing here. So it'll reach a cart, and these carts adds delay with micron precision. So they're very, very precise, and which will allow you to get very stable fringes. And I'll show you kind of the quick picture of what the cart looks like in a second here. But after the reflection of the cart comes in, we go into the front of the lab. So here's a picture of a cart. Here internally does a few more reflections within the cart as well. But you could see that kind of circled here, that basically they're on wheels and they're slowly moving across this these rails. Again, after light bounces off the cart, does again a few more reflections before finally it gets to the point in the lab where there are a whole bunch of different instruments for doing the science. And for my particular science, I use the MERC-X beam combiner. And so MERC-X, or the Michigan Infrared Combiner, in collaboration with Exeter, is the only instrument at the char array that you can collect light from 6 telescopes simultaneously. Any other instruments only allow for 2, 3, and maybe up to 4. So kind of just finalizing this light path here. There's a few more reflections internally within the instruments here. So this is all part of MERC. There's now the light is being fiber fed into this kind of box here, and then if you kind of believe me, there's a camera here on the very, very back. So again, MERC observes in the H band. There are kind of future upgrades to MERC that will extend this to J band, and other instruments will be coming online later to observe in even more wavelengths. But just note that for one specific observation, one given baseline, you don't just get one interference pattern. You get actually multiple interference patterns, anywhere from 12 to 32 or 38 spectral channels, really depending on what mode you use and the conditions of the night. Okay, so we get these interference patterns. What do they kind of look like? They could look something like this, depending on the instrument. Here, I'm kind of just showing a crude fringe, a crude plot of a fringe here. And so what's so useful about these fringes? What useful information can you get? Well, there's this, the Vanzi-Terra-Zarnicki theorem basically states that you could take the fringe amplitude divided by the average intensity of this fringe to get something known as a visibility. This visibility is essentially a sample in the Fourier plane. And so if you really think about it, an interferometer is now just sampling, getting samples of your object in the Fourier plane, and you're not getting actual images. So what can, for example, a star might look like in the Fourier plane or in the frequency plane? You have what I'm showing here, two different images. On the left, I have a nice model of a star here that has uniform intensity. And then I take the Fourier transform. And then so here on the right, you're essentially looking at an airy disk pattern. So you see now you're going from something on the angular size up on the sky to the frequency plane. So you get a whole bunch of different frequencies. And I'll kind of explain what these frequencies show in the next slide. But really, just kind of one important thing to note here is that the intensities differ depending on where you are on this frequency plane. So here in the very center, you get the maximum amount of the intensity that you can get, and then it goes to what we call nulls, and then rise up into different, kind of go on forever, kind of creating this pattern. Okay, so we have an idea of what we observe in the frequency plane. So where does Chara come into play here, and where do these baselines kind of fit in with all this? So again, I have the Y configuration I have highlighted here for Chara, but now let's just take a specific example of a baseline and kind of point out where this kind of lands on the Fourier plane. So for my example here, I'm just going to select S1, S2. Where does this land in the frequency plane? Well, because it's a very, very small baseline, it lands very close to the very center. Remember that lambda goes as, the resolution goes as lambda over baseline. So this means that for a very small baseline, you're really just looking at the low frequencies. And if you're looking at something like an image, this just is getting the overall shape of your object. Of course, what I have plotted here is just more baselines, depending on, you can make a whole bunch of different configurations. And if you use the full subset of the array, all 6 different telescopes, you get up to 15 different baselines. And so you get a range from low to high frequencies. So again, these high frequencies, you go away from just getting just the shape. You start going to really resolving some finer details on the star. Okay, great. Now we have a picture of where we're landing in the frequency plane. We have an idea of what these visibilities kind of look like. How do they relate to angular size and some more important things that we need to get to imaging? Again, we get a fringe and we get these visibilities. Depending on the value of the visibilities, it'll tell you directly what the angular size of your source is. And here I'm just on the left, or on the right, sorry, I have a plot of the baseline of your interferometer versus the visibility that you measure. And so I have here plotted a star with an angular diameter of 1 milliarc second and another star with 3 milliarc seconds. And let's suppose we observe, we are doing a measurement with a 100 meter baseline. Depending whether you have a 0.9 value for your visibility or something like 0.3, it'll determine, well, do we have, a 1 milliarc second star, or do we have something a lot bigger? And so there's a lot more details to this, but kind of just note that the bigger that your star is in angular size up in the sky, the more and more information, the lower that your visibility is going to get for this, what I call the first slope here. Another, you get another quantity that's kind of important for this, needed for imaging. You also need to know a quantity called closure phase and how that relates to atmospheric turbulence. So this diagram here on the left, again, I just have my star here coming from essentially an infinite distance away, coming down as a plane wave. Once it reaches Earth's atmosphere, it gets messed up, so to speak, because we have a whole bunch of different temperature variations. And in the end, we have a whole bunch of different indices of refraction because of that. So by the time it gets to the ground, the light is not hitting the ground the same way as it reached the top of the Earth's atmosphere. So they're hitting a whole bunch of different directions. Now, if we look at the image or this schematic here on the right, again, we have the same source, and we just look at just telescope 1 and 2 here. Well, telescope 2 has a little bit warmer pocket of air because of Earth's atmosphere compared to telescope 1, which causes that delay. We have that a whole bunch of bouncing around because of Earth's atmosphere, so it slightly gets delayed compared to the first telescope. And so as a result of that, we observe something called, we get the phase, or something that's intrinsic to the star itself, plus the atmospheric turbulence that really messed up all of the light, the information quality that you see here. So if you just observe with two telescopes, you have atmospheric turbulence, and you're not able to really do a good job of kind of correcting for the Earth's atmosphere. But now let's suppose you have 3 different telescopes. You have what is known as a closure phase triangle. And if you take these quantities now, the phase for telescope 1 and 2, 2 and 3, 3 and 1, if you do a little bit of simple math, you'll see that all of these different phases, you get the closure phase is just the addition of all the individual phases of these 2 telescopes from your object. And essentially, the atmospheric turbulence is canceled out, so you don't have to worry about that anymore. So you could kind of think about it as a self-correction, so to speak. Okay, great. We have visibilities, we have closure phases. We're a little bit closer to actually getting, models and images. So here I have, again, the airy disk pattern that I have in the frequency plane, and plotted just an example of a snapshot of what frequencies Chara samples. And here on the bottom is, of course, that nice uniform intensity star that I made before. So it makes visibilities here. The top plot here are the visibilities. The bottom plot here are the closure phases. And of course, plotting here now the x-axis, just the spatial frequencies. So what this first lobe tells us, it gives us a good idea of the angular size, as we saw before with just the visibilities. But if we were able to get, if we have a larger star, we're able to get a little bit more information. So we have, this can give us information, something about, let's suppose, the limb darkening, for example, and really constrain how the intensity varies from the limb to, or from the center to the limb. And of course, the closure phases here, you'll see plotted, don't really change. Again, this closure phase quantity tells you something about the intrinsic properties of the star. And so here, because I have a star that's uniformly distributed in terms of intensity, there is no differences in the closure phase. So now let's make things a little bit more complex. Let's add a spot on the star, and therefore the Fourier transform changes. And as a result, not only do the visibilities change, but really the closure phases change as well. So what I want to show here is that closure phase is a measure of the asymmetric light distribution that you get from your actual source. And so we can't directly tell exactly what's going on here. I mean, in this specific case, we can, because I provided, the star with the spot. But if we have no other prior information, we just know that there's something interesting going on with our source, and that's about it. Okay, now let's start to model these things and how we actually get to our final product. Here, what I have shown is a model of Lambda Andromeda from a previous work. And they basically plot here the intensity and the limb darkening, along with trying to parameterize 2 different spots here on the star. And so what is a model very simply? It's just really looking at only a small subset of parameters. You only get, for example, the size of the star, the number of spots, where exactly are they oriented in this model in X and Y position. So again, maybe tens, maybe 20 parameters. Let's go a little bit further and try to make things a little bit more complex. Finally get to imaging. So what is imaging? Imaging is essentially taking that model, but now adding pixel to pixel variation. And so what you're getting here is now not just a few tens of parameters, but you're getting thousands of parameters, because think of every single pixel being its own parameter. And one of the best ways to kind of solve for these types of imaging techniques is to use stochastic methods to really try to find a solution. And most of these stochastic methods use some sort of gradient-based models to try to lower the fit of your model to your actual data. And now to kind of wrap things up and slowly kind of transition to the work that I've kind of been doing for my PhD, I'm kind of talk about how we've gone from this 2-dimensional work of modeling and imaging here on the bottom row to, you know, the more complex and the next steps. So of course, I need a test case to, you know, work on my software. So, which is why I'm using Lambda Andromeda. Let me kind of go over the limitations of why we don't really want to use 2 dimensions. As in the previous kind of images and models that you saw before, you really only have, there's no time dependence linked from one model to the next or one image to the next. So each model and or image is completely different to the observation that follows. Another thing is that those models and images are based on intensity and relevant intensity, not actual, not the true flux coming from the star. And so we need something a little bit more complex. We need the true 3-dimensional orientation up in the sky. We need a temperature map kind of depicting the effective temperature of the star, or, you know, the temperature of the whole surface, plus the limb darkening to kind of explain the relative intensity variation, and the stellaration, of course, some other parameters. So first, again, let's just start with modeling. And so what I've used for my work is, specifically for Lambda Andromeda, I use this 3-dimensional code called SymToy. And what SymToy does, it uses surface modeling, and it applies it with a Bayesian model selection. And specifically, I use a technique within SymToy called multi-nest. And so what this does, it really does a global search over all the parameters that you're trying to find and calculate the best probability for your model. And so what I have here shown on the right is kind of an example of this code. But really just this code is great in such a sense that it takes advantage of both the CPU in your computer, and if you have a graphics card, to really try to show you what model you're really looking at in real time. And so you could combine many different epochs together to try to tie together and get one full model instead of 6 different models, for example, in 2 dimensions. So why am I using such a complex code? Why do I need a global search? Well, let's suppose you're doing a 4-dimensional search for the stellar parameters. You're looking for inclination, the rotation period, the position angle, and the angular radius. But now you're also looking for, let's suppose the star has a spot. Well, that also has a change in temperature compared to the rest of the surface of the star, the location of the spot, and of course the radius of the spot. So depending on the number of spots that you have in this specific example, we have 2. So not only do we have the star as a whole, but now we have parameters for each spot itself. So you're now doing a 12-parameter search. And so if you're looking at just a grid-based search, you're really just varying one variable at a time, and that's going to take forever, which is why we use multi-nest to really optimize our search. So you may think, how exactly do we compare these models to our actual data that are visibilities that's in the Fourier plane? Well, it turns out that there is an analytical solution for pixels, which is essentially just a polygonal surface. So what we can do is take the Fourier transform of a pixel and directly compare them to the visibilities. And so we can get the temperature at a given pixel along with all the stellar parameters to get a good chi-square fit. And now that I kind of optimized all of my, let's suppose now I have a good model to work with, I can now start really doing three-dimensional imaging. And so before I go on to that, if anywhere are curious, there's this paper here, how they kind of describe taking the Fourier transform of these polygonal shapes. Okay, so here what I have on the screen is what I've kind of worked on, the software that I've most worked on through my PhD. And so initially, we just had this code with a star that's three-dimensional and spherical, but it wasn't really that interesting. As kind of shown in introduction, I'm looking at stars that have different geometrical shapes. And so what I implemented here was a star that is kind of oblate spheroid, and also I took that a step further and kind of started implementing row-shaped objects. So for star systems that may overfill its row slope and started pouring material onto its companion. So our code, again, because of the geometry here, is model dependent, but it does have multi-geometrical fitting. And the way we kind of fit for a really good image is we use a quasi-Newtonian method to kind of get our fits for our images. And like SymToy in the previous code that I showed before, SymToy, this also has time variable imaging. So you can choose to only have one epoch, or you can tie multiple epochs together to make a full map. And so what I want to show here is kind of before we had two-dimensional imaging based on intensity, but now we have a full map of the whole surface of the star. And so here in this movie, you kind of can see kind of the Lambda Andromeda kind of varying across a whole month of observations. So how do we get a good image? Do we just say, okay, we get a model and we compare it to the data? Well, not exactly. We need to have some sort of penalty function. Well, why? Okay, so first of all, we're kind of trying to optimize the best temperature map across the surface of the star. In order to do so, we need to minimize the chi-square, so the model to the data, but we also added penalty function here. And so I'll describe three different scenarios as I have up above for why we need this penalty function. What exactly is this penalty function? It's just really just this hyperparameter here, a constant, times the regularization. And I'll kind of go, in the next slide, I'll give an example of what regularization I use for my work. So let's suppose here I use a hyperparameter that is very, very low. So the image here on the right, and so I'm just kind of plotting here just angular sizes of this sample star here. This hyperparameter is very low. So essentially that means that you're not depending on the regularizer at all. So you're just chi-square dominant. What this means is that you'll get an overfit. You're overfitting the model to the actual data. This isn't actually realistic to any images that you'll actually see. And so this penalty function will try to allow you to get something more realistic. But let's go on the other extreme. Let's suppose now you have something where your hyperparameter is very, very large. And so it's not depending on the model anymore, and it's purely just depending on the regularization. So you essentially have a star that's kind of having its temperature kind of averaged out across its whole surface. So we need somewhere in between where we have a good balance between the chi-square and the regularization. And so this is, you your star that's kind of just right, where it's, you know, it looks fairly realistic. So how do we go about choosing the best hyperparameter? We choose a technique called the L-curve, and all we do here is plot the regularization versus the chi-square fit. And what this L-curve does, really simplistically, as the name applies, we take an L and we just kind of look at the corner where and find and pinpoint where where the regularization and the chi-square have a good balance before the regularization really kind of takes off and becomes really, really dominant. And the regularization that I use for my work is total variation. And all this really looks at is, if you look at a specific pixel, it'll look at its neighboring pixels and say, well, how much do I want to differ from my neighboring pixels in temperature or in intensity? And so if you have a strong regularization, then you will have more of a smoothing, and the gradient between the two will be not that much. But if you kind of have a smaller balance, lower hyperparameter, you can start to vary things on a local scale, but still have temperature changes on that global scale. So as a result, you could get something like this again. Here, kind of showing on the right the image of, or the temperature map of Lambda Andromeda, and a mole-wide plot kind of just taking the star and kind of expanding out so you could see all of its surface all at once. So, and we see here that, you know, most of the stars for Lambda Andromeda may actually favor a specific latitude here. Okay, what if you weren't really interested in about the temperature, but you were interested more about the intensity? Our code again does solve for the limb darkening, and specifically for our work, we use the power law in order to get a fit for the limb darkening here. And so all we do is just multiply by the limb darkening, and you get this image that you see here on the right. And so this is not the true intensities, but it's just a relevant intensity, hence the quotes here on the title. Okay, great. Let's kind of bring this all the way around. We got data from Chara, we got visibilities, we have closure phases, and we are ultimately able to get images for Lambda Andromeda throughout a whole month here. So what I'm showing here is different epoch, and 6 different epochs here. And you could see that if you followed a spot, for example, from one day to the next, you'll see that the spot actually crosses the surface of the star before it kind of hides around on the other side. So again, these are just the temperature maps and respective angular size. And here I'm kind of just showing the respective temperatures of the whole star and the temperatures of the spots themselves. So if you just for some results, I can calculate the angular radius of the star along with its orientation, like the inclination and the position angle. And given the distance to Lambda Andromeda using Hipparcos data, we're all actually able to get a physical radius with really good precision. I believe since interferometry is known to have really precise measurements for angular diameters or angular measurements of stars. And given spectroscopic data, we have also an estimate of the mass of the primary system. So all of these parameters are just for the primary. So why is this particularly interesting? Okay, well, you know, I took it from 2-dimensional to 3-dimensional. Well, in reality, this is just one of 3 interferometrically imaged RSCVN variables. So to my knowledge, there are no other interferometrically imaged RSCVN variables besides Lambda Andromeda here. There's also Zeta Andromeda and also Sigma Gem. And so I just recently published the results, and hopefully I hear back soon. And now let's suppose you, again, weren't interested in the temperature, but you were interested more in the intensity. Have the limb darkening here with its corresponding limb darkening coefficient for using the power law. So I kind of wrapped up this project here, and now I'm currently working on 2 different projects. One, I'll kind of go into here talking about rapid rotators. And so what rapid rotators am I currently studying? I chose a subset of the rapid rotators that you previously saw in the beginning of this presentation, but I also selected a few new ones. And my criterion here was that mostly based on the angular diameter. So we chose 1.5 milliarc seconds because if you were anything smaller than that, then you start getting to the angular resolution of interferometry, and you wouldn't really see, you wouldn't get a good picture of the actual surface of the stars. So which is why we kind of have a rough limit of 1.5 milliarc seconds here. The declination is just based on the position of Chara, and we have a limiting H-band infrared magnitude, just mostly based on the instrument itself. And so why am I doing new modeling and imaging for some of these rapid rotators that have been imaged before? Well, previous observations did not investigate the differences between gravity darkening and limb darkening. And also, previous observations got multiple observations from one day to the next. Actually averages out any time-sensitive features. So you really, why is this important? Well, again, these rapid rotators are spinning very quickly in terms of just a few hours to almost a whole day. So, which is why combining measurements of between different days may not be really a good idea if you have a lot of data for one night. Another thing that I'm going to be using, that I'm currently using here is I'm currently comparing these Ester models, which is a two-dimensional radiative transfer model, comparing to my Chara data. And so what I have plotted here is just the physical size of a 5 solar mass star. And what Ester does, it actually looks at the interior, tries to model what the core looks like, and all the way to the exterior of the star. And what you're seeing here is just kind of showing the differential rotation between the core and the surface, the poles and the equator here. So you could see here that the poles are just basically spinning more slowly, or at least in this top portion here. So what I'm currently doing is trying to adapt their esters improved von Zeipel law to ROT-IR. And we'll see in the next coming months what those results are. But of course, I've kind of already implemented some modeling within my imaging code. Remember, we can do modeling and then imaging as well. So here, what I'm trying to really disentangle that gravity versus limb darkening, and also if there are any time-sensitive, if there are any surface features on the surfaces of these stars, we can try to see if we can do any time-sensitive imaging. We may not expect any actual features different than the work that people have done before, but this is astronomy, and we always find new things every single day that we don't expect. And so through this kind of just movie here, I'm just showing the angular, just varying the different models of the stars through my ROT-IR code, and showing here on the bottom the omega, the critical angular velocity fraction, and up here the rotation period in days and the number of revolutions per day. So you can kind of get an idea of how fast these things are actually rotating. So, and also as a consequence, you could also see the gravity darkening effect here as well. And now for part 3 of my talk, I will kind of be wrapping things up with where can we take interferometry from now and within the next few years and the next decade or so. I got involved within a project at GSU called the Aries Project, or the Advanced Reconnaissance of Earth Orbiting Satellites. I've got interested in this project mostly because I wanted to get a little bit of a lab experience, and it's really like playing with very expensive Legos. So specifically what I'm working on here is looking at open air beam propagation. So as the name kind of implies, for the title of this project, we look at satellites. there are a lot of similarities between what the Air Force is trying to do at imaging satellites versus what we astronomers are trying to do. So things kind of go hand in hand. And I'll just be talking more about the astronomy side, but can answer any questions about the satellite stuff later. So what am I talking about? This open air beam propagation. So let's suppose on the image of the left here, you have a telescope, kind of how it's shown before, but now let's get rid of these vacuum pipes. And let's put them somewhere at the Char array. And if we were building a 7th telescope, let's put them somewhere. So we have, again, the Y configuration here. Let's put it right here in the middle, near the middle. Except now these telescopes aren't just stationary. Let's suppose you have this telescope that's now moving on rails. And so what this allows you to do, it's now starting to spin it along the middle and propagating the light through open air. And so why is this important? What's so special about kind of doing this? Specifically for interferometry, you kind of have here for the stationary telescopes, you have the sample of the UV plane and their specific, their respective frequencies that you're measuring with the baselines. But if you were rotating now that telescope, you start to observe, get a lot more frequencies here. And this, given more observations, you can start to fill in an inner part of the UV plane. What is this somewhat similar to? Again, this is just kind of a rough example, but this could be very similar to something like a 30-meter telescope, where the interior acts like a 30-meter telescope, but you still have those very, very large baselines, kind of giving you the finer details of if you're trying to image objects. So let's suppose you're trying to observe Betelgeuse. This image here that I'm showing is an image made by Alma in the sub-millimeter regime. That inner annulus will roughly get the overall shape, right? So the low frequencies get the overall shape of the star. But now this is Chara, we have those long baselines. We can now observe those high frequencies, gain really details of the surfaces of stars. So we can, maybe one example could be, we could really start to image the surface of Betelgeuse very, very well to really great detail. Let me take you now through a tour of what we're kind of trying to simulate in the lab here. So here what I have, we have a laser being fed through a fiber, and we're basically shining through a few different optics here until it reaches this metal slab here. And what we have here is this metal slab has 2 different pinholes. Those pinholes act as 2 different apertures or 2 different telescopes. And so they're trying to simulate a 2-telescope interferometer that's trying to propagate light through these rails. So they propagate light through here, and it kind of show on the bottom here the light path, but it's the same light path, very similar light path on top. Go through optics here, and they finally reach through these objects called SLMs. These SLMs are really just simulating Earth's atmosphere. After they bounce off, they finally reach these deformable mirrors and the combination of these wavefront sensors of the adaptive optics system. And these 2 correct for any atmospheric turbulence made by the SLMs. So what we're trying to simulate here is, we have moving telescopes that we can get better UV coverage for, and depending on where those telescopes are, we can get better resolution and ultimately better images of these stars. So we're trying to simulate here the turbulence of horizontal beam propagation and see if we can actually try to correct for this future new concept that nobody has really tried. So again, now after it's being corrected by the AO here, it's being sent back to the back, and we get something that looks like this. So this is just kind of a first glance here. But what I'm showing here are basically these 2 columns here. The columns on the left is showing perturbations of the atmosphere at an R0 of 20. So the seeing parameter here, or for those of you that work in long exposure photometry, we get a full width at half max, about half an arc second or so. and then slightly worsening conditions here. So we basically make turbulence a little bit worse. And so this first row here is just that uncorrected. There's no adaptive optics correction here. It's just what the fringes would look like here. And you see some sort of bending here on both sides, a little bit worse here on the 13.5 are not phase that we're injecting onto the SLM. But after we close the loop on both sides, we see that we get straight fringes. So again, this is just first results here. And I currently have another paper in the works to try to get some results within the next few days. I'm going to end my talk with some of the VR applications that I've done here at Georgia State. I've been working on this three-dimensional code, RotaIR, that does models and imaging. Well, this is a really good transition for trying to put this in a three-dimensional scope, which virtual reality does a really nice job is trying to handle 3D objects. So this is supposed to be a movie, and hopefully it'll play in the next few moments. But we thought of the idea of, well, why don't we take these images and these models that you could get from Chara and take that to outreach events to show the public what we've been doing at these interferometers. And I've also been, I took an example of this VR, one of these VR headsets to the last winter AAS meeting in Hawaii. And we actually got really good reception of this. So because based on the way this works, we can actually see, we can have the star spin, we can have, you could click on different cells on the star and look at the specific temperature of that cell based on the type of star that you're kind of looking at. And so before I showed it's like the rough image of the Lambda Andromeda. Here you were just seeing the rapid rotators, and now this is kind of these row of objects for binary systems. And if you so wanted, you could look inside these stars here in the star 4, if they have anything interesting going on, if we actually had good models of that. So I'll end my talk there, and with this kind of just summary slide here, and I'll look forward to any questions.
Great talk. Thank you so much. So if there are any questions from the audience, you can put them in the chat, is the easiest thing to do. So while you're doing that, one thing I was wondering, Arturo, I noticed we have some students, even undergraduate students, in the audience right now, and I was wondering if you would mind if you have any advice. Right, you're about to finish you're defending in the spring, right? Do you have any advice for students who are planning on applying to grad school?
Yes.
For Calbridge scholars? Yeah, that'd be great.
The first advice would give would be to not really be afraid of asking questions. So it's kind of took me a while to learn how to ask questions and not really be intimidated. My undergrad advisor did a very good job of kind of breaking my shell. So I think he prepared me for grad school. And I think that I think asking questions isn't a good thing, and don't be shy of asking what may seem like a stupid question, because I personally think that someone else in the room might have the same exact question, but they just don't really want to answer or don't want to ask that. That would be my first thing that comes to mind.
I think that's great advice. I still struggle with that today, but it's true.
Yes.
So it looks like, can you see the chat? Looks like there's one question that came up. I could read it if you can't see it.
Yeah, so do you consider using maximum entropy method for the regularization, and are there any advantages or disadvantages of that? I haven't personally worked with maximum entropy. My PhD advisor is more of an expert on kind of the different methods. I've kind of just only looked at, for example, total variation, looking at the L2, the different norms, the L1 norm, the L2 norm specifically. So I haven't touched on that specifically just yet. So I'm sorry, I can't really answer that question just yet since I don't have the experience.
Great. I'll also mention, sorry, I said to put the questions in the chat, but we actually have a Q&A, which I think is a better way to submit questions so everyone can see them. But
Okay.
There's one more question by Alex Rudolph. I don't know if you see that, Arturo.
Yes. Do you have any reflections about leaving California for your PhD? Looking back, I think it was a very good opportunity, and I'm very grateful that I was given the opportunity to go to a PhD program. And of course, it gave me a little bit more freedom, but it really, I can just to kind of write things up there. I really like the direction where I went with my PhD. I'm happy with the advisors that I work with. So for me personally, I think it was a very advantageous opportunity and fantastic opportunity.
Great. So we're just over 5, but maybe if there were any final questions. If not, then I guess we'll thank our speaker, our final speaker of the semester. Thank you so much for that excellent talk.
Oh, we have one more question here.
Okay. Sorry.
Eric, yes, Lambda Andromeda is a binary. So I did actually look at the secondary, try to detect the secondary, and some rough calculations actually came out that the flux from the secondary was about 0.1% the flux ratio from the primary. So that in combination with the angular diameter of the secondary, I don't remember the angular diameter on top of my head of the secondary that I estimated, but the combination of both kind of led me and my collaborators to believe that we weren't able to detect the binary at all, just because it's so small and especially very, very faint.
Could you say any more about the brightness limit on this interferometer for doing other work? You could imagine imaging planets in our solar system or galaxy centers.
Yes, good question. So I specifically work with, the only imaging camera that we have right now is MERC-X. And so based on the adaptive optics and some of the internal optics within the instrument, we've actually raised it from what it used to be before, around 6 magnitudes in the H band, going up to now around 8. So we can now start to observe, I know some MERC-X collaborators and also Exeter people that have are starting to image, what is it, T-Tauri stars or some other objects, but as opposed to like planets, I'm not so sure that that's still, I think the frequency, the flux ratio, I think would be too much as of right now. But I know that this current work with Classic and Climb, which is another instrument at Chara, that is looking at AGNs and the cores of AGNs and are a lot fainter than this. So Classic and Climb can go up to, I think, a faintness limit. I may not be entirely correct, but I think it's a few magnitudes higher. 12, 13, something like that. I can't really say, so yeah.
Okay, thanks.
Mm-hmm. Any final questions? All right, well, I guess we'll thank our speaker one more time, or Aaron and I will do it on behalf of everyone. So thank you so much. Great talk, and good luck with finishing up your PhD and everything going forward, and hope to see everyone when we start again next semester.
Thank you for having me.
Yeah, thank you.